Good morning. I think we can start the talk. My name is Chen, and I'm just the interpreter guy yesterday. And I'm from Baidu SRE team. I currently work on data mining and machine learning things. So we are trying to use this kind of technologies to solve the SRE problems. Today, I will represent the SRE team to talk about our work on combating against the flood of the alerts. During the previous 2 years, the flood in Baidu actually reaches a very high level. The engineer usually receives more than 130 alerts each day. If we divide these alerts into daytime and nighttime, he will receive more than 100 alerts at daytime and more than 30 alerts at nighttime. Here we define daytime to begin from 7 a.m. to 0 a.m. in the next day, and the nighttime is the rest of the time. If we translate that into the frequency perspective, we can see that the engineer will receive one alert every 10 minutes in the daytime and one alert every 14 minutes in the nighttime. So if you think that 130 is not very large, but if you look at the frequency, it's actually quite large. So I don't think so that our system is that bad, because actually Baidu provides quite stable and consistent service to our customers. And I don't believe that our engineers can handle this every alert seriously because of this kind of high frequency of the arrival of the alerts. So I have to assume that the alerts have a lot of redundancy inside. So we done a simple investigation, and this investigation shows that in all the alerts that we send SMS to our engineers via mobile phones, only 15% of the alerts are actually essential and effective. So this confirms that our conjecture that a lot of redundancy is inside the alerts. So we decided to do something to reduce the redundancy. But interesting is that not all of the engineers agree with this perspective. For example, one engineer actually said that he doesn't want to remove those redundancy because when he is on duty at night, he needs to hear more alerts to be fully waken up. So actually he needs more alerts. This is what we need to consider because this point seems to be legitimate. We actually do more investigation among these data, and we find out there are 4 major observations. First, we find that there are around 58% of the total alerts are duplicates. Duplicates are actually a very common phenomena in the monitoring system. This is because the monitoring system will evaluate the alerting rules in a periodical manner. So if the underlying issue just don't appear, and the rule can generate those alerts repeatedly, right? So a few of the engineers actually, they try to embed complex logic in their alerting rules, trying to remove those duplicates. But the rest of the engineers just leave it there and ignore these duplicate alerts. Another complex duplicate form is that an underlying issue actually can cause a lot of alerts from different rules and modules. So in this case, we try to group these alerts together and remove these duplicate alerts. So this is the first thing we try to do, is to group them. And secondly, we also estimate the attention ratio that measures how much alerts have actual follow-ups. And the result shows that the attention ratio is actually not very high. For example, at nighttime, it is only around 25%. We know that during the nighttime, the delivered alerts are actually have relatively high importance levels. Otherwise, people will not think that they need to be delivered at nighttime. But such a low ratio of the attention means that a lot of these alerts actually have their importance level overset. Therefore, we define a set of standard and alert delivery behaviors, and also we try to persuade the engineers to calibrate the importance levels according to the perceived attention ratio. Third, we find that quite a few alerts have more than 5 receivers. On average, each alert has 3 receivers. We are quite surprised that we need so much receivers for the alerts because we know that in most of the case, only one engineer is enough to solve the problem. So this implies an ineffective on-call procedure. And in addition to the management adjustments, we also developed a tool that to support on-call schedule and also the escalation mechanism. At last, we find that there are around 88% of the alerts are just at the instance level, which is the smallest granularity in our deployment, and of which 40% can be resolved by simple operations. So we try to implement an automatic self-healing mechanism into the monitoring system to satisfy those requirements. When the self-healing is activated, there is no need to deliver the alert anymore. Ideally, these self-healing mechanisms can actually remove 35% of the alerts. In the following, I will introduce all of these solutions one by one. So first, let's look at the grouping method. For the alert grouping, we tried actually 3 methods. The first is just using the simple method to remove some duplicates. These duplicates usually are generated by the same rule and from the same module. There are also cases that alerts from different rules and modules are related to each other. So grouping them requires a different method. A side benefit of this grouping across different modules is that it can actually reveal some information of the underlying issue, and sometimes it is helpful for the engineers to locate the problem and solve the issue. Another case is that when the network connectivity breaks and the alerts usually surge, we specifically design a way to detect the connectivity of the network inside the data center and try to suppress the alert surge. The simple method actually groups alerts based on their natural attributes. The first natural attribute is just the rule name. And we actually, in most of the time, we require the alerts to be grouped together to belong to the same rule. And another perspective is the deployment structure. Because Baidu use virtual machine technology in their deployment system extensively, so the deployment structure includes the logical levels and also the physical levels. The logical levels includes just products, modules, clusters, and instance. And the physical level includes data center and machine. When to perform this grouping, we usually require the alerts to be generated by the same rule. One exception to this requirement is that if these alerts are generated by the same instance or generated by the same physical machine, we allow them to be grouped together even they come from different rules. This is because multiple alerts from different rules in the same instance or physical machine actually implies that there is something wrong in the whole instance or in the whole physical machine with its hardware. Although this method is actually quite simple, it represents a lot of engineers, their experience and idea to remove the duplicates. In order to achieve this result, here we show a result of the grouped alerts. This message is a little bit messy, but we can still find something inside it. First, there is a rule name. And the first part of the rule name is actually the column before. The part before the first column is the namespace of this rule. And the second part with the red one is the level of this rule. And we can see that this is instance level. And the last part is a rule name. And this is actually a fatal level rule. We can see that this is a instance level alerts. Then we comes a ratio. The ratio means that it comes from a cluster. Actually, this message contains 2 alerts, belongs to 2 instances in the cluster. Because the cluster contains around 150 instances, so the ratio of the alerting instances is around 1.36%. The next is the alert duration. This is because that the underlying issue actually is transient and it disappears after 1655. So the message tells the engineer that the 2 instances just recover after this time. At last, there is a link with more detail is provided, so the engineers can access more information through this link to a web page. In order to accomplish the grouping effect, we need to design the following procedure. Here, when an alert is triggered, we just put it into a linear buffer instead of just deliver it to the users immediately. Every alert rule has its own linear time, specifying how long it can stay in the linear buffer. After an alert in the linear buffer expired, we need to deliver it to the user. But in addition to this alert itself, we also try to deliver other alerts in the same linear buffer and group them together. In the example here, the alert in the first line has expired, so it's in red. And suppose, according to our grouping policy, the A column rule 2 in the second line and A column rule 1 in the fourth line can be grouped together. Therefore, the delivered message will contain 3 alerts. And 2 alerts remain in the linear buffer after this delivery. Here, the A, B, C before this column actually refers to different namespaces, just like the example in the previous PPT. Besides this simple grouping method, we also implement other methods. A common practice in system design is that we try to divide the system into modules and deploy the modules in a distributed environment. And then the modules communicate among each other through network, usually in the form of remote procedure calls. Suppose here module A calls module B. So when module B encounters a problem, it is very likely that both module A and the module B generate alerts. To reflect this situation, we try to obtain association rules from the alerting rules history. What we do is that we divide the alerting sequence history into a set of transaction windows. Each transaction window starts from a specific instance of an alert and with a fixed length. Then we can compute the probability of a rule, suppose this rule Y, who appears in the transaction windows starting with another rule, suppose it's rule X. And if this possibility is high enough, we just conclude that rule X actually is likely to lead to rule Y. Then, when we grouping the rules, we can allow that when the rule X is delivered and there is another alert in the linear buffer from rule Y, we can group them together. So, why we need to mine this association rule from the alert history instead of just using this call graph? The reason is that it's not always that when B encounters a problem, it will cause A to generate alerts. So we actually need to capture which kind of alerts in B will trigger alerts in A. We believe that the alert history can tell us this information. Another problem is that association rule is actually not strong enough to represent causality. So if we want to use these association rules to tell us that what kind of issue exactly caused this kind of failure or loss, it is not strong enough. And our experience shows that using this to perform such as diagnosis or something else needs a lot of actual work to perform. But as for what we now focus on is that to remove those duplicates is enough. For example, let's look at an extreme case. suppose rule Y is not properly configured. So rule Y constantly generates alerts, right? So if we will just look at any kind of rule X, we will see that rule Y appears in rule X window with high probability. So we decide to absorb rule Y via every possible rule X. In the case that we try to remove the redundancy, this is okay because rule Y is not properly configured. But if we try to infer the causality of the different modules, this is not appropriate. So this is the limitation of this method. Another situation is that network issues can actually cause the alert to surge. This is because when the instances in the subnetwork are disconnected, all the other instances that depends on this subnetwork actually can be affected and hence generate a lot of alerts. We observe that when such a surge happens, the alerts usually covers a lot of different rules and also different products. So we just use this heuristic formula to measure the coverage of the alerts. This formula is actually the geometric mean of the ratio of alerting rules and also the ratio of alerting products. As an algorithm guy, I actually not quite happy with this formula because the mathematical foundation is unclear. But it's very strange that practically it seems to be work well in our environment. The plot below shows the curve of these scores on a lot of the data centers. Each curve is actually a data center. And we can see there are 3 spikes in the plot. And truly, these 3 spikes correspond to 3 network failures in 3 different data centers. So when the score is high, we will group these alerts together and tell the on-call engineers that there's probably a network connectivity issues. So the alert surge will be suppressed. So one problem of our alert grouping mechanism is that is about the linear buffer. The linear buffer requires that a extra delay for each of the alerts. Although we allowed users to specify different linear time for different alerts in order to incorporate their consideration of the alert importance. But there are still engineers complaining about the decreased timeliness. So we are still searching for better ways to balance the timeliness and the effectiveness of the grouping method. As we have mentioned in the beginning, the attention ratio of the alerts are actually quite low. We use the following method to estimate the attention ratio. For each alert, we examine whether there exist certain actions in the time window after the alert is delivered. The action could be a number of different things. For example, the user maybe just access the monitoring system, such as reading the detailed information of the alerts or just viewing the relevant curves. And the action could also be the logging operation into relevant production machines. If any of these actions exist, we just regard the alert is taken care of. Otherwise, we regard that the alert is ignored. This method can actually clearly display the degree of attention ratio at the nighttime, but it doesn't work at the daytime. This is because at the daytime, the engineer will perform various actions based on various reasons, and probably the action does not reflect that he is taking care of some kind of alerts. But even with this kind of limitation, we can still estimate a lot of the alerts attention ratio. Let's remember that every engineer will receive 130 alerts each day, and 30 of the alerts happens in the nighttime. So it covers more than 25% of all the alerts. So we believe that attention ratio could be a good reason and guideline to calibrate the importance levels of the alerts. And then we define 4 importance levels. Each level is associated with a different alert action. For the critical level, in addition to send a text message to on-call engineers, we also make phone calls to ensure their attention. Remember in the first, I talked about the guy who cannot wake up at night with just a single alert, right? So, of course, SMS is not strong enough to make him woke up, so we just make a phone call. So the time should be long enough. And for the major level, we will send text message only, but if the alert is not handled in some time, it will be escalated. Escalation will deliver the alerts to more people, and its mechanism will be introduced in the following slides. For the rest of the 2 levels, the delivery actions becomes even lighter. Then we try to ask the engineers to calibrate and change their importance level according to the attention ratio. But sadly, many of the engineers just refuse to lower the importance level. So we just have to turn to our managers to do something. They take various management methods, which is, I don't know, just to push the engineers to make sure that the ratio and the importance level should be consistent. And the escalation mechanism actually comes from the observation that quite a few alerts have a lot of receivers. We find that a lot of alerts have 5 people, and this large setting is like this. First, there is a primary on-call engineer who is in charge of this duration of on-call. And there is a secondary on-call engineer who will be helpful if the primary engineer cannot respond to the alert quickly. And then there is an engineer lead who is in charge of the specific module or subsystem. And one senior engineer who can give the technical advices when the underlying problem is hard to resolve. And then there comes a manager who will decide what to do if technically we can do nothing, but the impact is large enough. So in most of the time, actually, the primary on-call engineer can solve the problem, but anyway, this alert goes to all of these receivers. So we think that there should be something to be done. In addition to optimize the on-call procedure in the management perspective, we also provide a tool to support alert escalation. In this tool, each alert will go through a series of stages. The first stage is actually fixed. This is for the primary and the secondary on-call engineers. When an alert is delivered, the primary and the secondary engineers will always receive the alert. Of course, in many situations, the alerts don't require a secondary engineer, so the secondary one is actually optional. Then there could be 0 or more escalation stages. If the alert is not claimed or solved in a specific amount of time, it will be escalated to the next stage, in which more people will be notified. In our experience, we find that one fixed stage and one escalation stage is actually enough for most situations. So here is an example of the interface of our escalation design tool. The figure shows that there exist 2 stages at the lower part. The receiver of the first fixed stage is a group named sharp Z ODA and something, and the receiver of the escalation stage is ODA. The sharp Z ODA group in the fixed stage is actually a special one. It not only contains a set of engineers, but also a on-call schedule. The schedule is shown in the top part, and we can see that there are 4 engineers. Each of the engineers will be in charge in 1 week. With the help of this tool, the engineers not only design the escalation stages, but also schedule their duty time. In this example, actually, I just deliberately forget the last part of the sub-Z ODA group name. And the last part of this is actually the pinyin of the routinely meeting. So we actually use this tool to try to book the meeting rooms in our weekly meeting in Baidu. Perhaps you don't know that Baidu's meeting room is always not enough for us. So we have to put something special in each week to try to grab the meeting rooms. So if the guy fails to book a meeting room, we will notify all the attenders that every of the attenders will try to help this guy to book the meeting rooms. But there should be a penalty here. If the guy fails to do that, we actually make a Coke rule. If the guy fails to book the meeting room, he will buy a can of Coke for every attendance of the meeting. So with this punishment, the guy will try his best to solve the problem. And I believe that the engineers may use the same kind of mechanisms in their management methods. And the last one is the automatic self-healing mechanism. We find that there are actually 35% of the alerts are for only one instance and can be resolved by simple operations. For example, some engineers used alerts to purge excessive log in a lazy way. What they did is that they just set up an alert on the free disk space, and when the alert is triggered, he will log on to the machine and remove some old logs from the machine. To satisfy such requirements, we provide a callback mechanism. This mechanism is actually embedded inside the monitoring system. When defining the rule, an engineer can actually specify a callback action. This action can be to restart some process or delete some old files or something else inside the instance, or it can be a complex one. So in this case, he will perform an RPC call if the action is very complex. RPC callbacks are usually suitable for module-level cluster or cluster-level alerts because the related healing operations are usually quite complex, so they need to be designed carefully and to be executed in a separate location instead of inside the monitoring system. If an alert has a callback action, then the action it will be invoked automatically when the alert is triggered. And then the alert will not be delivered to the receivers, but we allow the engineers to view the alert log in the monitoring system. This log will present the log information as well as the execution result of the callback actions. So previously, I introduced 4 of our actions in combating against the alert flood. All of them are just mainly focused on the technical direction. But I still want to emphasize here that the management support is also very important in our effort. For example, we need the manager's help to lower the importance levels of the alerts. And in on-call escalation, we also need the manager help to improve the attention ratio at the first fixed stages. Otherwise, the alert will go through the following escalation stages, and the alerts will be delivered to all of the people. So here is the result of our comeback. This figure shows the number of alerts in each week, starting from, I think it's 2015. The shaded area indicates the period that we gradually deploy our alert reducing methods. And we can see that after the period ends, the total alerts decreased by 85%. So this is a huge decrease. And in this talk, I introduce our method to fight against the alert flood. The methods include grouping, importance level calibration, escalation, and the self-healing callbacks. The effort not only reduces the number of total alerts, but also helps our engineers to understand the root causes of the issue better. And another thing I want to mention here is that this combat is not just in the technological side, but also relates to the management side. And also, there must be some trick in product design. For example, we make the phone calls to engineers when they are at night, on duty at night. So this is I think it's a combination of all the possible ways to solve the problem. So this is all for my talk. Thanks for your patience.